Hello, good morning, everybody. I am Ignacio Esquivel from Universidad Politécnica de Madrid, and it is a pleasure for me to introduce you to Prince ANANDARAJAH, who is currently lecturer in the School of Electronic Engineering at Dublin City University, and also director of the Photonics System and Sensing Labs. He has been a pioneer in the field of short optical pulse generation and optical frequency comb generation from semiconductor lasers, paving the way for application in optical communication and optical sensing. He holds international patents, and as a good entrepreneur, he has founded Pilot Photonics, a spin-off company. The title of his talk is Multi-Carrier Transmitter and Multifunctional Demultiplexer for Next Generation Network. Prince, thanks a lot for accepting the invitation to participate in OPTOEL, and it's your time for the presentation.
Okay, thank you very much, Mr. Chairman, for the kind introduction. As introduced, my name is Prince ANANDARAJAH. Okay, and first of all, I would like to thank the conference organizers and especially Professor Esquivel for the kind invitation and giving me this opportunity to present some of our work at this esteemed conference. So the title of my talk this morning is Multi-Carrier Transmitters and Multifunctional Demultiplexers for Next Generation Networks. At this juncture, I would like to thank all my co-workers and mention that the work was carried out at the Photonic Systems and Sensing Lab in the School of Electronic Engineering at Dublin City University, Ireland. So at this juncture, I would also like to say good morning to all the ladies and gentlemen who have joined, and thank you for attending my talk. So let me first of all give you an overview of my talk. So it's as follows. I'll start off with a brief introduction where I'll kind of generally talk about optical frequency combs and how these combs can be employed in telecommunication networks. Okay. I'll then talk about the specifications of the optical frequency comb, so the properties that it must have to be employed in telecommunication networks. Okay. I'll then move on to talking about the optical frequency comb generation techniques, but I'll be focusing on the gain switch technique due to time. Okay. And when I talk about this gain switch technique, I'll be presenting some key characteristics that the optical frequency comb possesses. Then I'll go through some previous work where we kind of have instances of integrated optical frequency combs using this technique, how we can expand such a comb, and finish off with that. I'll then move to talking about this active demultiplexer, okay? And how this is related is that if you want to use an optical frequency comb in a telecommunications network, then you need to demultiplex all the lines and use them as individual carriers, okay? So there's a particular type of demultiplexer, which is the active demultiplexer that I'll present, its characterization, and then finally its implementation in a system. I'll then finish off with a few brief conclusions. So let's start off with a very general introduction, right? Talk about optical frequency combs, and let's start with a very simple definition for an optical frequency comb. So it's a signal whose optical spectrum consists of equidistant lines, okay? And if I can change this to a laser pointer. So here you see kind of these equidistant lines of a frequency comb, right? That's your frequency axis, and you have these lines. And the biggest property that an optical frequency comb has is that it can be used as an optical ruler. What does that mean? So if you look at the spacing between these lines, they're quite precise, they're fixed. Okay, just like a measurement ruler where you have lines that's fixed. Okay, and because of that property, you can actually measure unknown frequencies by taking two tones and beating them, and using that beat note, you can then measure unknown frequencies. Okay, and because of these properties, optical frequency combs find themselves applied in many, many different applications. Okay, I've mentioned a couple here, or a few here: frequency metrology, high precision spectroscopy, optical fiber sensing, telecommunications, and you can keep going, right? I mean, dual comb spectroscopy. You can talk about time and frequency metrology. You can talk about optical clocks and so on, right? Many different applications. So they're very versatile. One of the things that I wanted to mention early on, right, is that the parameters that the frequency comb shows or possesses depends on the nature of the application. So if you're using it in telecommunications, the kind of parameters that the optical frequency comb possesses could be slightly different from when you use it for high harmonic generation, like generating millimeter waves or terahertz and so on, right? Okay, so this being an optical communications conference, I don't actually need to say it here, but I thought I would kind of just share with you the prevalence of fiber optics in telecommunications, right? And that's kind of clearly focused on by this particular chart, where we see kind of fiber being prevalent in terms of undersea connections and communications, right? Not only do they connect kind of cities, countries, but also continents, right? Now, if we have so much fiber, then why are we talking about kind of, again, using optical frequency combs and telecommunications and so on? So one of the reasons is because of the growth in new services and broadband applications, okay? And I've shown pictures of a few here. These, because of kind of their bandwidth intensive nature, they start putting a lot of pressure on our existing networks. And believe it or not, we are actually kind of coming to facing a capacity crunch. We're running out of bandwidth, okay? And obviously, it's not helped by streaming videos like this, right? And this will be kind of very familiar to the audience here, and maybe good memories of where Spain beat Croatia in the recent Euro Cup, right? And I've gone on to the next round. Okay, so if fiber is prevalent and we're running out of capacity, let's first look at what we could do, right? Use the existing infrastructure and see what we could do. So the type of infrastructure that we have now, okay, it's fixed by this kind of organization, ITUT, right, is that we have wavelength division multiplexing, so multiple colors being transmitted, each carrying data. But they are slotted into a fixed grid that is spaced by 50 gigahertz. So one channel within 50 gigahertz, and the next channel within the next 50 gigahertz, and so on, right? So multiple colors, each transmitting data. And I have a legend here to kind of show the different types of data that people are aiming for nowadays. Okay, the problem here is that once we kind of go to high data rates and keep the legacy channels like 10 gigabits together with, let's say, 100 gigabits or 400 gigabits, we end up wasting a lot of space. Okay, so one of the propositions to move forward is this kind of move towards, if you look at the middle picture here, the flexible grid. Okay, so we change and reduce, or we kind of change the granularity of this fixed grid and make it a flexible grid. Okay, so shown here is 12.5 gigahertz, but you can go to 6.25 gigahertz as well. And then what you can do is take a bunch of them and you can then use any of these. So you kind of waste less space. Okay, and this kind of is what I want to focus on in terms of my talk today. There's also a push towards a completely gridless architecture where you can save more space, okay? But that's just for information today. We can kind of maybe talk about that another day, or you might hear this at a different conference. Okay, so if we're to use the 50 gig grid, currently in industrial networks, this is the scheme they use, right? So here's our 50 gig grid. We have different colors showing the different channels, each carrying 100 gigabits of data, right? Supported by different lasers. There can be lasers integrated in an array, but they're different lasers. The fact that they're individual lasers, there's a problem, right? The fact that these lasers actually start drifting in wavelength. It's very difficult to accurately control. That causes cross-channel interference. And because of that, we need these black rectangles, okay, that are called guard bands. And that space is wasted, and it reduces the spectral efficiency that we can get from the system. So if you actually use an optical frequency comb that we have defined, okay, and get rid of these array of lasers, the immediate advantage is that you would be using, let's say, a single laser or a couple of lasers to generate multiple wavelengths that multiple lasers give you here. So straight away, you're gaining in terms of cost and potentially energy efficiency. Okay, fine. Apart from that, one of the major advantages of using the optical frequency comb as a transmitter is this kind of feature that the OFC possesses, which is the precise wavelength spacing. Okay, so they kind of stay fixed. And that means that you don't have to worry about these drifting into each other. So you can either reduce or get rid of the guard bands. And usually at this stage, we kind of reduce it drastically and place the channels much closer together. So you improve the overall spectral efficiency, and you get this spectral saving where you can put more channels. For example, if you're going to watch then Spain in the quarterfinals, right? So you have adequate capacity then. Okay, so let's kind of look at the optical frequency comb closer now. So we talked about kind of how it can be employed in a communications network. We'll talk about a frequency comb and its desired properties. So typically you want a large number of lines, let's say over the entire C-band that we use nowadays, possibly beyond that. You want some flexibility in terms of the free spectral range being tunable, the spacing between the lines, right? So you want to make it smaller, you want to make it bigger, depending on the network itself, okay? You might have heard about kind of elastic optical networks, and this comes in very, very useful. You might also want to change the central emission wavelength, okay? So that might be a desired characteristic as well. What you would also want is narrow optical line width on each of these tones, okay? Especially if they're going to carry higher order modulation formats, okay? You're going to modulate the phase and the frequency, then you would need narrow optical line width. The phase correlation between the lines is not overly important in general telecommunications, but for example, in radio over fiber applications, that might become important where you generate kind of millimeter wave or terahertz frequencies, right? So this line is highly phase correlated, let's say, with this line and this line, okay? You want a high optical carrier to noise ratio, and you want to achieve all this at low cost, and you want to achieve it in a small footprint, okay? So it should be optically or photonically integrable. Okay. So in terms of generating optical frequency combs, there are many different techniques out there. Some of the most common techniques, right, of OFC generation are based on mode lock lasers, so semiconductor lasers or fiber lasers, electro-optic modulators, micro-ring resonators. But for my talk today, I want to focus on the gain switch laser itself. So gain switching, right, essentially is a very simple technique. It's cost efficient because it involves direct modulation. You choose a commercially available single mode laser. In conjunction with a DC bias, you apply an amplified sine wave and you can get out a frequency comb, right? And it's quite flexible because you can tune this modulation frequency and you can change the spacing between the comb lines. So here's 8.5 gig comb that's shown by simply modulating it. Right? Now you can achieve a simple comb or simple technique to achieve a comb, but you have disadvantages as well. As you can see here, there's kind of an amplitude ripple, right? Poor spectral flatness. the line width of each of these comb tones could be pretty poor, because if you take a commercially available kind of, let's say, a DFB laser that can have a line width of, let's say, 1 to 2 megahertz, and when you gain switch it, that gets slightly worse. It can go up to about maybe 4 or 5 megahertz, right? You also have a limited number of comb lines. It's a direct modulation approach, so the bandwidth of the laser would kind of limit the number of lines. However, you can kind of avail of a little bit of complexity, and you can then address all those problems, overcome those problems. So you use a high purity master laser, if it's tunable better. You inject light, so external injection of light into your slave laser, and what you get then is addressing of most of these problems. So shown here in blue is that particular comb, and then you have everything in green. So everything is fantastic. You get better frequent free spectral range tunability, wavelength tunability, better spectral flatness, as you can see here, much narrower optical line width if this is spectrally pure, because you pass on those properties to the slave laser. You get a larger number of lines and much better optical carrier to noise ratio. Okay, and there are just a couple of publications, one from my esteemed colleague who is the chairman here. Okay, his group published something recently, and we started working on this quite early on, right? And there are other papers as well, lots of other papers. I think there's another group in Madrid who actively publish on gain switching using VCSELs and so on, right? So this is just a sample. Okay, let's very quickly look at some of the characteristics that are useful in telecommunications. So as I said, you want some level of programmability, some level of flexibility. So the spacing between the lines can be changed, right? So easily changed from 1.25 up to 12.5, the same laser, just by changing the modulation frequency. You can also change the central emission wavelength. Okay, if you use a Fabry-Perot laser, choose different modes, inject into that. Here we show 30 nanometers of tunability. You can get up to 40, 45. We've shown that previously. Okay. Other characteristics, you can pass on, as I said, the purity of the master laser. So if the master laser has a line with less than 30 kilohertz, each of the optical tones can kind of possess the same thing. So this is an FM noise spectrum where we can deduce the line width, the optical line width, and we show that the master drags the comb lines as well to it, right? If we look at the relative intensity noise, or the RIN, okay, it's really good. It's much better than minus 145 dB per hertz. Okay, really good for intensity modulated systems, on-off keying, PAM4, and so on. Also, the phase correlation, okay, as I said before, if you're generating kind of millimeter wave or terahertz frequencies, then you want to take two tones and beat them together, and you want a highly pure beat note, right? So here you see different frequencies, and this can extend up to terahertz, okay? So we start with a comb at 6.25, and you can see that we focus a lot on 6.25 as a base rate because of the flex grid that I talked about earlier. Okay, so when you beat those two tones, the optical phase noise cancels and you get a very pure RF tone. Okay, so that's kind of some key properties that have been demonstrated over time. I also wanted to kind of quickly talk about this kind of smaller footprint, right? That's important for kind of commercial adoption, right? So early on, we showed a two-section laser, master and slave, both active, and with injection, you can get kind of a reasonable comb. Another two-section laser, in this case, one is passive, one is active. You gain switch the active. The passive one can be controlled with bias in terms of feedback, so it's kind of a self-seeded approach. You can also get a decent comb, okay? And this was also kind of published early on with some modulation on some of the lines in JLT, right? Then more recently, a member from our group kind of enhanced this laser to a four-section laser. And that gives you better control of the wavelengths of the master and the slave. And here again, you have a reasonably nice comb, and that was used with some data transmission and reported in the Photonics Journal. Okay, so integration is very well possible and is active at the moment. Then the expansion, right? Compared to other techniques, one of the problems with the gain-switched optical frequency comb is that you get limited bandwidth, spectral bandwidth. So simple techniques like using a phase modulator after the gain-switched laser, you can enhance the spectral occupancy by 2, okay? So expansion of ×2, very early publication. Then you can use more complex techniques like highly nonlinear fiber, and you can get 5 to 10 times the original bandwidth. Okay, and that's also an early publication from our group. More recently, one of our group members kind of used an architecture that is photonically integrable, right? So multiple stages of gain switch lasers go through a modulator, and then you phase correlate them in an SOA, and you get about 3 times expansion from the original. More recently, the same person is now working on a mutually injection locked scheme, right? So 2 gain switch lasers that have an overlapping spectrum, you inject in the middle so they get phase correlated, and then you can expand it. And using the scheme, he gets about 3 times or 3.5 times the original bandwidth as well. And he hopes to report this soon. Okay, so with time, let me move on to now talking about the next concept. So this is an optical frequency comb-based wavelength division multiplex transmitter that would be used, right? Typical architecture that would be used. So here we have the OFC, which we have talked about. Okay, again, I talked about gain-switched optical frequency combs, but any particular OFC can be used. But then in telecommunications, you would want to demultiplex each line so that each one will act as a carrier, right? So each line would then be modulated. And if the loss of the demultiplex and the modulator is high, you might need amplifiers after each stage, okay? Typically, they're combined and then amplified here. This is the worst case scenario, okay? So this is what I want to focus now in the remaining, let's say, 9 to 10 minutes of my talk. The commercially available demultiplexers are shown here, right? One of the most common ones is a wavelength selective switch. You can recognize this as coming from Finisar. This is an arrayed waveguide grating. This can be fiber-based, but the one shown here in the picture is a free-spaced one from Kilia. Okay, and then this is an extreme case that can be used in labs, not commercially used. It's a narrow band filter that's wavelength and bandwidth tunable. Okay, so in all cases, you see the spectral resolution. So this is the minimum bandwidth that you can kind of filter out, right? 12.5, 12.5, and in this case, 6. But this is not a commercial solution, just in the labs. So if you have a 6.25 gigahertz comb, you're going to struggle to filter out individual lines using this, right? Also, the insertion loss is very high in each of these, okay? And then you have the filtering loss. And in all these cases, you might need amplifiers to follow the demultiplexing, okay? And the modulator, for example. And that means that you're degrading the OSNR. Okay, the optical signal to noise ratio is already being degraded at the transmitter. So what we propose is to use a multifunctional, active demultiplexer. So this is what we have, but we are proposing to use a technique such as this, and I will talk more about this in the oncoming slides, right? This technique was initially proposed by researchers in UCL kind of early on for radio over fiber experiments, but we have gone on to then use this in regular optical communications and use the demultiplexers as multifunctional devices, okay? Essentially achieve demultiplexing, modulation, amplification, and so on. Okay, so let's look at how this happens. First of all, the demultiplexer that we use, the active demultiplexer, is based on an injection-locked semiconductor laser. So it's a regular semiconductor laser, and it's injection-locked by the comb lines. Important thing is that the spectral resolution is in megahertz, and it's multifunctional. It can be used not only as a tunable demultiplexer, you get some wavelength tunability. It can also be used as a low noise amplifier. The amplified spontaneous emission that's added on when you amplify is very low. You can also use it as a power equalizer. If you have a power ripple, as I had shown before, you can equalize that and get equal power in all the tones, meaning that each of the channels is going to give you similar performance at the receiver. Not only that, you can also use it as a modulator. So there's one component that's giving you multifunctional kind of tasks, if you want, or satisfying multifunctional kind of tasks. But the most important thing is that after achieving all this, it still kind of maintains the properties of the optical frequency comb, phase and frequency of it, okay? And more importantly, this architecture can be photonically integrated, okay? So you can get a small form factor, and that has been done by one of our industrial collaborators of recent, okay? Okay, let's look at this kind of a little bit more closely. So here's our optical frequency comb, simple splitter, two-way kind of demux if you want, okay? So the optical frequency comb goes through a VOA, gets attenuated, okay, so that we get very little power being injected, and you don't have to use an attenuator. If you have more stages, the split loss will take care of that attenuation, okay? This red line is the demux laser in CW mode, okay, so just DC biased. We inject into that. We tune the demux, okay, and then it's injection locked by the required comb line. And you demultiplex that out and leave the others. So same thing here, you can demultiplex another line using that same approach, okay? Just to introduce two kind of acronyms here. So one is this comb line suppression ratio, which is the chosen tone, the power of that against the unwanted tones, okay, that just pass through. Also, the injection power that is put into this demux laser, we refer to that as CLP or comb line power, okay? Okay, again, very quickly, here's a comb at 1.25 gigahertz FSR. Pass it through a WSS, you can clearly see the lack of resolution, okay, bandwidth resolution or frequency resolution, lots of lines selected. Even if you use this extreme case of a filter, lots of lines. And in our case, with the active demultiplexer, we can pick out a single line with a good CLSR, okay? Okay, so here's our comb, the experimental comb at 6.25 gigahertz FSR, okay? Here's the demux laser that's CW, run in CW mode. And then we have this comb attenuated, so pretty low power. And here's the demultiplexed line. Okay, so good CLSR, we've suppressed the other tones, and we can then modulate this down. Okay, so there's details here again in these publications from our group. Just to say that, you know, I talked about programmability of the frequency comb. So here are different FSRs. Whatever the FSR is, you can still demultiplex tones from them with good CLSR, okay? Comb line suppression ratio. So no problem at all in kind of selecting them. But what you can also notice is that you can pick out lines. Typically in a telecommunication system, you pick lines only 3 dB from the spectral peak because you want kind of uniform performance of these comb tones. But in this case, because we use this demultiplexer that amplifies, okay, and balances out the spectral ripple or the power ripple, you can then kind of even filter out lines that are 20 dB down. So in a way, that's like expansion or power equalization, right? So you can go from 26 to 36, 8 to 13, 4 to 7, 3 to 5, and so on. Okay, so you see the amplification, the low power that's injected, and you get about, typically, even though there's an attenuator on the OSA, so that's why it's showing less than 0, but it gives you about 7 dBm. That's the output power of the CW laser. Okay, now for the other functionality. So I've shown you how you can demultiplex, how you can amplify, how you can equalize the power. Now to show you the modulation function, right? So here's kind of our demultiplexing setup. We then, because you have a semiconductor laser here, we can then directly modulate that as well. So here we use on-off keying at 10 gigabits per second, directly modulated. So just to kind of quickly show you, that's the optical frequency comb, okay, 12.5 gigahertz in this case. Filter out 2 lines by using the demultiplexers, and we modulate 1 line at 10 gigabits per second. So that's the modulated spectrum. We transmit it over fiber. I think it was 3 kilometers, so it's aimed for kind of intra data center applications, direct detection, and then we get error-free performance, okay? More information in this publication here. More advanced formats, okay, again, direct modulation, 2-channel system here, optical frequency comb, 2 lines selected. What we do here is 1 line is modulated with 4 QAM and 16 QAM discrete multi-tone signals, okay? So we can achieve, if it's 4 QAM, we can achieve 12.5 gigabits per second on each tone, or 25 in the case of 16 QAM. Okay, transmit it over fiber and then detect it and do offline processing. Okay, in this case, so the parameters of the DMT signal is mentioned here. I won't kind of run through it because of time. I have about 2 minutes left. Okay, I just want to talk about the multiple channels. So we kind of superimposed 9 different channels. Okay, so if you use 4 QAM, you get 12.5 gigabits per second on each wavelength, and 25 gigabits per second per wavelength using 16 QAM. So you can get more than 100 gigabits using this, or 200 gigabits using this, the aggregate capacity. Okay, results are shown here. 4 QAM, you can easily achieve less than FEC and transmit over 40 kilometers. Okay, so it can be used for inter-data center as well. And we chose different lines, okay? So the middle comb line, but a comb line that's at the extreme, so 20 dB below the spectral peak, but because of the power equalization and the amplification, you can still get good performance from that. Okay, there are some constellation diagrams back to back and after 25 and 40 kilometers. That's the 16 QAM, again, good performance and constellation diagrams from there. Okay, and just to kind of finish off, I just wanted to say we have kind of implemented that same experiment, 4 different channels demultiplexed from the optical frequency combs. Okay, comb, sorry. So 4 channels shown there. Each one is modulated with this discrete multi-tone data, directly modulated, okay? You see equal power, modulation, demultiplexing. Transmit over fiber, you can pick different bands of channels, or if you had more stages, you could achieve higher capacity, okay? Or larger aggregate data rates. Transmit over fiber and performance, we got excellent performance. Okay. Okay, so to conclude then, right? So I talked about optical frequency combs, and because of certain properties, they're extremely attractive for multiple applications. Okay, and I focused on one application today, which was telecommunications, and talked about the typical requirements that the optical frequency comb needs to portray. Okay. Amongst the different optical frequency comb generation techniques, I focused on gain switching and showed you how the externally injected gain switch laser can be optimized to be used in systems. But to be used in systems, we need to avail of a demultiplexer. And if we're going to a lower granularity, like 6.25 gigahertz, then we need to avail of some technology. And if that technology can give us multifunctional characteristics, that's fantastic. And that's what I shared with you, its characterization and its implementation in a system. Okay. And for those who are working in this particular field with optical frequency combs, just to kind of keep you encouraged and to let you know that you should aim for the skies. Remember that it led to the awarding of a Nobel Prize for Hansch, okay, for his work and Hold's work on optical frequency combs used in spectroscopy. Okay. So to acknowledge the funding agencies, I would like to kind of thank Science Foundation Ireland, Enterprise Ireland, and the Higher Education Authority. okay, for funding this work. And just to say that this is kind of the discrete setup that we use in the lab. But as I had mentioned, this whole thing, this is a comb and a demultiplexer fully integrated with the electronics, the drive electronics, and a 4-output channel, right? And that's been realized by an industrial collaborator in a project. So all that's left for me is to thank you very much for your kind attention, and I'll hand over back to the chairman. Thank you.
Thank you, Prince, for your nice talk. Very, very interesting. You have wonderful results in communication during last time. So I appreciate a lot your talk. Now it's time for question. The main audience, I can transmit you some questions from people. You can see in the chat. The first one is that they say that the speaker has shown that the line width of the frequency comb lines is smaller than 30 kilohertz. I would like to know how this measurement were performed. And second, how this line width depends on the laser diode type. I mean, if there's a DFB or Fabry Perot laser.
Okay. Thank you, Chairman, for the question. So yeah, that's a very good question. So first of all, there are many different ways that you can use to characterize the line width. So nowadays, there's expensive equipment that can do it for you, but not all the labs can afford that. So we go with kind of tailor-made test beds to do this. The simplest technique that can be used is kind of the delayed self-heterodyne setup, okay, where essentially you split the kind of signal that you want to measure. You decorrelate it after going through a delay, you offset it in kind of a frequency, combine them, and you can measure the beat tone, and that gives you an idea of the optical line width. Now, even though that technique is quite popular, sometimes it tends to hide information, right? So if you want to look at where your noise is coming from, which frequencies are contributing to it, then you want to use a different technique. And what we use is called a modified delayed self-heterodyne technique, okay? And if the person who asked the question is kind of interested, I can share a publication from our group on that particular technique. And what that does give you, what that gives you is the FM noise spectrum. And from the FM noise spectrum, you look for the white noise portion, the flat portion, and that gives you a value of S0. And by dividing that by 2, you can then kind of infer the actual optical line width. And that's how we measure whatever we measure. So for example, we measured 30 kilohertz in our case, right? So, and again, the second part of that question was quite interesting as well, how do you get 30 kilohertz, or what determines it? It depends on the kind of master laser you use. So you can use kind of long cavity semiconductor lasers, right? So for example, if you use a discrete mode laser that's made by Ablana Photonics, they have kind of, let's say, 750 micron cavities, or even 1 millimeter cavities that can give you line widths as low as maybe 500 kilohertz, or even a little bit lower. So you can use that as a master laser, but then the master laser is fixed. You don't get wavelength tunability. So your comb won't be wavelength tunable. So instead, what we do in our group is that we use semiconductor-based tunable lasers, okay? So they're based on these so-called M-core engines. It's very common, so you can get it, for example, from Pure Photonics nowadays. They sell these lasers, and they're tunable, and kind of some of the more kind of pure lasers can give you line widths in kind of the low kilohertz range, right? And that's what we use. So without kind of dither and so on, you can get down to 10 kilohertz. And if you use, for example, a fiber laser, you can even get down to the hertz level. So it's up to you what level of complexity you want to have in your system. So if you want to photonically integrate it, then it's important that you have a semiconductor laser, right? That can be photonically integrated with the rest of your optical frequency comb components. So I hope that answers the question.
Okay, thanks a lot, Prince. We have got another question from Juan Ignacio Garcés from Universidad de Zaragoza. He says, thank you for the really interesting talk. What can you say about chirp characteristic of the wavelength log relation used to modulate the signal in the transmitter?
Yeah. Okay. Very good question. So again, the chirp characteristics here in a gain switch laser have been studied over a very long time. So I mean, going back a long time ago, without giving out my age, think about kind of gain switch lasers as pulses, right? And the fact that gain switching involves changing the gain or kind of driving the signal in such a way from kind of virtually below threshold to above, you essentially incur a lot of frequency chirp, right? So, I mean, typically you can get up to maybe over the pulse duration, up to 150, 160 gigahertz of chirp. Now, depending on how you inject into it, so if we come back to kind of the frequency comb, so we go to the spectral domain, depending on how you inject, you can then really bring that chirp down to very low levels. So in one of our kind of early publications, a photonics journal publication in 2011, if I remember right, we showed that the 150 gigahertz of chirp across the temporal duration of the pulse can be reduced to something like, less than 10 gigahertz, right? You can reduce it further as well, but obviously then you don't get the broadest comb possible. So we kind of rely on the chirp a little bit in terms of kind of having a broad comb. Now, in terms of transmission, how that affects your particular kind of system is a little bit different. So you're not kind of transmitting pulses in this case, right? So if you transmit the entire pulse, so if you're using return to zero modulation or formats, then you would kind of suffer from the chirp kind of due to the dispersion effects, right? But here you're filtering out each individual line. So the chirp effects are not felt drastically when we use it in kind of an optical frequency comb concept. So, but it's a very good question. I hope that answers the question.
Okay, Prince, thank you very much.
No
I have a very short question because we have only a couple of minutes. You mentioned that the multiplexer, the commercial multiplexer approach has high insertion losses, but your solution, your proposal is dividing the original comb between the number of lines. So we have four wavelengths, you have 6 dB, but 8 wavelengths, you have 9 dB. So this is increasing with the number of wavelengths. That's right?
That's an excellent point. So yes, that's very true. So if you want to go to 16 wavelengths, then you have to consider the division, and you have that amount of loss. But actually that loss is very useful in your system because the amount of power that is required to injection lock your demultiplexer is really low. So we get kind of comb line suppression ratios, which is dependent. I didn't share that result, so we have a kind of a characterization of that as well. Is dependent on the comb line power. So the lower the comb line power, the better the comb line suppression ratio. So an optimum level is about minus 30, 35 dBm. So if your comb has so much power, you can split it by lots of stages.
Okay, thank you very much for your answer and for your talk. Thanks a lot. We are finished now. Bye.
Okay, thank you very much, Ignacio. Thank you. And thanks to everyone. Bye.